The method of images. Suppose a point charge Q is held at a distance d above an infinite grounded conducting plate. What is the potential in the region above the plate? It's not just here for a Q. We will reduce a certain amount of negative charge and on a nearby surface of a conductor. The total potential is due in part to Q directly and in part to an induced charge, to this induced charge. But how do we calculate potential when we don't know how much charge is induced or how it's distributed? Our problem is then to solve Poisson's equation. And the region for Z is greater than 0 with a single point charge Q at the coordinates Cartesian here 0, 0, D, subject to the boundary conditions given here, V equals 0 when Z equals 0 and so on. And by Pythagoras here. Now, the first uniqueness theorem guarantees that there's only one function that meets the requirements. Now we take 2 point charges plus Q at the point here and negative Q at this point here, which is basically a reflection, negative D and positive D, and no conducting plate for this potential is given here, which we'll call equation 1. Now the denominators represent the distance x, y, z to charges plus Q and negative Q. So it follows that here we get these conditions where V equals 0 and Z equals 0, and our second condition V goes to 0 as our x squared plus y squared plus z squared is much greater than d squared. Now, and the only charge in the region where Z is greater than 0 is the point charge plus Q at our coordinate here. But these are conditions of the original problem. The second configuration, exactly same potential as first. In the upper region, Z is greater or equal to 0. The lower region, where 0 is greater than Z, is different. The potential of a point charge above an infinite grounded conductor, where Z is greater or equal to 0, is given by equation 1. And the uniqueness theorem certifies it if it satisfies Poisson's equation in the region of interest and assumes the correct value of the boundaries, then it must be correct. Now, induced surface charge potential. Now we know the potential. It's straightforward to compute the surface charge sigma induced on the conductor, as we've established this before. This is our del in a specific direction. Now, which gives rise to the normal derivative, which is the normal derivative of potential at the surface. In this case, the normal direction is in the z direction, so we get this here. Now, from equation 1, again, we'll get this. So our charge on the xy is given by this, as expected. So the induced charge is negative, assuming a positive charge, and the gradient x equals y equals 0. Now let's compute the total induced current Q equals our integral of our surface charge over an area. The integral over xy plane could be done in Cartesian coordinates with our d of alpha equals d of a equals dx dy, but it's easier in polar, where r and phi. So our area in polar is here. So by giving in polar coordinates and integrating is straightforward, and we get the negative Q. The total induced charge on the plane is thus negative Q. Now, the force and energy. The charge Q is attracted towards the plane because of the negative induced charge. We calculate the force of attraction since the potential in vicinity of Q is the same as the analog problem one with plus Q and negative Q but no conductor. So also is the field. Therefore the force equals this, where as usual our hat denotes a unit vector, directional. Energy, however, is not the same with 2 point charges and no conductor. Now our work is given as such, but for a single charge on a conducting plate the energy is half of this. So why half? Energy stored in the fields is here, our work. In this case, both upper region Z greater than 0 and lower region 0 is greater than Z contribute by symmetry. They contribute equally, but in the second case only upper region contains a non-zero field, hence the energy is off. We could determine energy by calculating work required to bring a charge from infinity. The force required to oppose electric force is thus here. So we'll come to this conclusion. As I move a charge Q towards a conductor, I do work only on Q, on that Q. Now please do like and subscribe, there's plenty more to come.